So what happens when we let one audio frequency modulate a second one? In the previous video, I made an amplitude modulator from a diode switch. The amplitude of the guitar signal was modulated by a control signal, and the diode switch became a kind of voltage-controlled amplifier. Now for this video, I'm making a ring modulator from just a few components, namely 4 op-amps and 4 diodes and a handful of some common resistors. Now ring modulation is interesting because it mathematically multiplies the two signals. Unlike the amplitude modulator, a ring modulator allows the modulator to swing both positive and negative. And for this reason, it's often referred to as a 4-quadrant multiplier because both the modulator and the carrier can both swing positive and negative. Okay, I have to disambiguate some of the stuff here. Now, ring modulation is also described as a gritty approximation of a 4-quadrant multiplier. And to confuse things, a 4-quadrant multiplier is often referred to as a balanced ring modulator or balanced modulation, or, my favorite, the over-modulated amplitude with phase inversion. Anyway, it all points to the same thing. It's all ring modulation. So, ring modulators, from what I've seen in my research, tend to be just passive circuits, and they use 2 transformers and a ring of diodes between them to create the ring modulation effect. So here's a typical schematic of what a ring modulator looks like. I have a version of that circuit here, and I will have links for these in the description below. So let's give a listen to the passive ring modulator, and I want you to notice a couple of the drawbacks. So note the problems. We have signal loss due to the forward voltage of the diodes. So the guitar signal is a little bit attenuated, but you'll really notice that the carrier signal bleeds all the way through to the output, and it can get really, really annoying. Now, 4-quadrant multipliers tend to be active circuits, and they use a set of amplifiers where the carrier and the modulator signals can swing positive and negative again. But many of the circuits that I see for 4-quadrant multipliers or ring modulators, again, they accomplish this by using special purpose chips. Now, for example, Craig Anderton's fantastic book, Electronic Projects for Musicians, he builds a ring modulator in Project 9, or as he describes it, a balanced modulator, but he's using a special purpose chip, namely the NE565 or the LM565 phase lock loop. Now his project worked great and it sounded really alien, but I don't particularly like having to use special purpose chips. So, back in 2019, I ran across a paper by a fellow named Sebastian Azevedo. Apologies if I've got your name wrong. And he wrote a paper, an easy 4-quadrant multiplier using a quad op-amp. I'll leave a link to his original paper and to a demo of the circuit that he made below. So I want to build a version of his circuit with a few minor changes, and I want to step through the thinking process in his paper because this is really the only technical paper that I have seen the description of what a ring modulator is and how it actually works. And it's pretty interesting when we get to the end result. All right, stepping through Sebastian's paper, he starts off by looking at this amplifier here, And at first thought, you might think that this is a diode doing some clipping and some amplification here. It's not a clipper. What this is an antilog amplifier. The diode is acting as a voltage-controlled resistor. Now, I know that I've talked in the past about how diodes, depending on the voltage that we have applied to it, the amount of current coming through has this exponential curve. And we can express that in terms of a resistance by doing some differential equations. Now, what is pretty creative about Sebastian's solution is that he puts two of these together, where if the voltage of a signal is positive, it's going to go through one of these antilog amplifiers, and then he's going to send it through another resistor pair. And this is just a garden variety an op-amp inverting amplifier. So positive signal comes through, we get this antilog amplification out of it, and then it gets inverted again. If the signal is negative, we still do the antilog calculation, but now both of these are the same polarity, where this is positive, it gets inverted and becomes negative, and then it gets inverted again and it becomes positive. This starts off as negative, it's inverted and becomes positive. What we wind up doing through this circuit is we wind up coming up with something like this, where when our input voltage is positive, the result is negative. So we're actually going to be down here, but I'm also sending it through this inverting amplifier, so it becomes positive again. For the negative input voltage, I still do my antilog function, but negative, it's inverted, and I get a positive result. So since these curves are exponential going both ways, this actually forms what's called a hyperbola. And his argument is that, yes, it's a hyperbola, but for small signals, quote, the hyperbolic characteristic is indistinguishable from a parabola or square law relationship. In other words, at a small signal level, this is close enough to a parabolic function. So in other words, this is like a square function. So if I go up in voltage, the output is basically a square. If I go down in voltage, even into the negatives, I also get the square, and it's a positive. Now, for me, it's a big leap of faith because I haven't bothered to do the Fourier expansion, so I'm just going to accept it on faith and move forward. All right, so the clever part of his solution is he takes a look at this equation. A plus b squared minus a minus b squared equals 4ab. And we can ignore that number 4 there and just consider the fact that I have the sum of two things squared minus the difference of the same two things squared, and I wind up getting the product. So what that suggests is that if I do the sum of these two squares, all I've got to do is come up with another circuit to produce the sum and the difference of my two signals. Well, that's pretty easy, you know, especially using an op-amp. This is what a simple adder does. I add two signals with all these resistors matching, and I get A plus B. And then I can take that result, send it to another op-amp with twice this other signal, and I get the difference, A minus B. So to build the circuit, he does recommend using precision resistors. He does recommend using Schottky diodes, and he also recommends using low offset op-amps. I didn't do any of that stuff, but what I wound up doing is building his circuit here I have my two inputs, and I produce the sum, and I produce the difference of the two signals. And lo and behold, we have our diode ring again. So if it's positive, it goes through this top leg, through this op-amp. This produces my antilog output. If this branch is negative, it goes through, and I still perform my antilog function, but then I invert it. So this is my parabolic function here. And then I have my difference input, A minus B, and the diodes are reversed. So I perform my antilog function on a negative signal, and if it's positive, I go through, perform my antilog function, invert it, and add it, and then I have my product coming out. What's interesting about this is that the diode ring appears in the circuit, and it's not out of a design rule. It's not because we're making a ring modulator that we put this in here. It actually fell out as a result of the mathematics and our function, a plus b squared minus a minus b squared. And the fact that we have all four of these diodes here, I can handle cases when a plus b is positive or a plus b is negative, and invert it. And I can also handle when a minus b is negative, because I'm subtracting the squares. And if this is positive, I perform it and invert it again. Right, so building up the ring modulator, I've got my new test harness here. Just giving it a quick buzz test. This is going to be my guitar input. Got the output going to my test amp, and I've got an oscillator coming in through the external input. Okay, so I know I'm getting a good clean signal all the way through. This design of the ring modulator uses a total of just 4 op-amps, and I'm using a pair of LM358P that I've had in my parts bin for quite a while. So LM358, these are both dual op-amp chips. So I'm going to quit talking and just do this, and I can fast forward through the boring stuff. All right, construction is finished. It's fairly quiet. Let's get the guitar plugged in. That is incredible. see, let's frequency step. Yeah, let's do 1 hertz. That's cool. So now, instead of doing 440, I'm going to do A220. So since I have the frequency generator set up to play an A note pretty much, anything that I play in the key of A is more or less going to sound harmonious. Like there's an A, there's a fifth, an E. What else we got here? A D. Ooh, that's nice. So this has absolutely been one of the most technically dense videos that I've done to date. And please let me know, is this too much in the weeds? Most people don't go into details of how things work. And in a way, I feel like I want to do this kind of stuff in future videos. I do want to dive into equations and explain why is it that I'm making the circuit the way that I am. I think there's value in that because it helps us to develop new circuits. And in particular, the reason why I wanted to make this, not because I wanted to make a ring modulator, because they're kind of ugly, and I know you can set them a certain way and you can have them sound like a pretty ugly fuzz effect, or that it adds those weird overtones. That can be cool, but what I'm really trying to do is I'm trying to mimic the equations that come from amplifying from a simple triode. I stumbled into some other equations about 2 years ago, and in order to solve this through a computer program or through equations, it really just comes down to a quadratic equation. And if you set it up right, you get these beautiful even harmonics, just like you get from a triode. So that's ultimately what I'm trying to do here, is I'm trying to tweak a ring modulator just to use it as a multiplier to compute a quadratic equation in order to mimic the overtones that you get from a tube amp, all using just a couple of diodes and a couple of simple op amps. Anybody could have done this, but they just haven't. So either I'm some freak of nature and I have discovered something that no one else has bothered to do, maybe, or this is a fool's errand. I don't know. If you're interested in figuring out, or if you're interested in finding out where this whole experiment goes, do consider subscribing, and please let me know if this is the kind of level of detail and stuff that you're interested in as well. Also, let me know if you spotted any errors. Let me know if you have stumbled across something else that does something like this already. So let me know, because I'd love to hear about it. And anyway, thank you for stopping by, and I will catch you guys in the next video.